Good morning, everybody. Our lecture is on vapor compression refrigeration system, VCRS. I say vapor compression refrigeration system. So later we'll discuss about vapor absorption and other systems. So first, let's start with vapor compression system. So vapor compression system, we have seen that one compressor must be there, then compressor condensing refrigerant, and you have one condenser to throttle valve to your evaporator to compressor again. Okay, this cycle you must remember. So this is condenser. This is not compressor, this is evaporator. This is condenser. This is throttle valve. Okay, so fluid will be flowing in this loop, in this direction. Now you have seen the different refrigerants. We have seen the different refrigerants and their names. And refrigerants normally will be like R112, 134A, or water can be refrigerant, or ammonia can be refrigerant, your carbon dioxide can be refrigerant. So there are different types of refrigerant. So for our specific purpose, for example, if I give any problem to solve for one refrigerant cycle to calculate heat and other thing, then refrigerant name also will be given, because different refrigerant will have different properties. So you cannot use the same property for all the refrigerant. So water will have certain property, ammonia will have certain property, or R11 will be certain property. So based on the property, we'll have to calculate. So let's go to basic of thermodynamics. Reversed heat engine. So we have temperature T1, we have W, we have Q1 coming, Q2 plus W, and this is Q2, and it is going to T2. And this section is taken from your PK-NOC book. Okay, and chapter I think 14, you can go through this one. So this is the reversed heat engine, reversed heat engine. So reversed, so COP. So this term coming Q1 by W equals Q2 by Q1 minus Q2. So COP means coefficient of performance. Coefficient of performance. Okay, COP of heat pump refrigeration. So Q2 by W. So you should not get confused. This is first one Q1, second one is Q2. So Q2, Q1 minus Q2. Okay, and Q1 equals, if I draw this TS diagram, compressor again I have to draw TS diagram. Okay, this throttling process, then evaporation process, this one going like this, and TS diagram, TS 1, 2, 3, 4. So TS diagram again, vapor envelope you draw, 1 is here, 2 is here, 3 is here, 4 is here. Okay, now T1 S2 minus S3. Q1 is heat addition. Okay, so numbering is something wrong, so we have to correct the number. 2 is here actually, 2, 3, 4, this is 1, so numbering have to change, 1, 2, 3, 4. Okay, so S2 minus S3, S2 minus S3, this is your heat addition process, and the Q2 equals T2 S1 minus S4. W net power, WC compressor minus WE equals Q1 minus Q2 equals T1 minus T2 S1 minus S4, because okay, Now T1 temperature of heat rejection. So T1 equals temperature of heat rejection. T2 temperature of heat absorption. Okay, so COP heat pump reversible equals Q1 by W net equals T1 minus T2. COP refrigeration reversible Q2 W net equals T1 by T1 minus T2. So COP HP reversible 1 plus 1 equals T1 by T1 minus T2 minus 1. This is not plus 1, this is minus 1. So this is giving T2 by T1 minus T2 equals COP refrigeration reverse. Okay, so therefore COP HP reversible equals COP refrigeration reversible minus 1. Okay, so you should remember, if HP is given, so refrigeration of COP, coefficient of performance value, also can be found. Here one thing is there, coefficient of performance does not mean this is efficiency. Efficiency is different thing, coefficient of performance is different. Efficiency means like compressor efficiency will be there, your whole system efficiency you can calculate, but COP coefficient of performance is that how much heat you are transferring, so that it is indicating, it is not indicating the losses in compressor and other systems. So COP can be more than 1 also. Okay, vapor compression refrigeration system or vapor compression refrigeration cycle, VCRS also you can say. Okay, this is cycle or this is system. So sometime I am using VCRC, sometime VCRS, SYST. Okay, now again draw this cycle diagram, compressing. So it will be like compressing, then your condenser is here, condenser means heat is getting rejected, then you have evaporator here, evaporator will be taking heat Q2, you have throttle valve. Okay, now you should put arrow symbol 1 2 3 4. Okay, so TDS equals du minus VdP, you know that. So S4 minus S3 equals P1 P2 VdP T. Okay, and if I see this part, this upper part is high pressure part, these are high pressure, and this lower part low pressure. Okay, upper part high pressure means after compression the pressure is high, and it will be, the high pressure will be there till throttle valve. After throttle valve your pressure changing to lower pressure. Okay, so pressure change is happening in between these two. Okay, and below this one actually low pressure. Okay, so I can say like this, low pressure and pressure change happening. Now this one I want to draw in PV diagram. So PV diagram is constant pressure pulses 2 to 3. You see 2 to 3 constant pressure pulses but very high pressure. Okay, 2 to 3 high pressure, 3 to 4 what is happening, pressure change is happening. So volume also changing, pressure also changing, and 3 to 4, 4 to 1, 4 to 1 again constant pressure pulses, 1 to 2 again pressure changing. Okay, so if I ask you to draw PV diagram, so you should be able to draw this one. You must put arrow symbol, you must put proper numbering. Okay, Now same thing, if I draw in TS diagram, already you know that one, TS, right? Then it is happening like this, 2 3 4 1. Okay, on the saturation line, so that must be, it must be 1 here. Okay, now HS diagram, HS, so pressure line is here. Okay, so 3 is here, saturation line, and my 2 will be upper here, the 2 to 1, 1 to 2, 1 is here, 3 to 4, throttling happening, so enthalpy constant, I said enthalpy, isenthalpic process. Okay, 3 to 4 and 4 to 1. Okay, so if I ask you to draw HS diagram, so 3 to 4 will be horizontal line because it is isenthalpic process, we are not changing any energy there. Okay, so performance and capacity of vapor compression plant or vapor compression refrigeration cycle or system, if you can write, if is okay. So PH diagram they have drawn like this. This is critical pressure. Okay, so critical pressure knowing is very important because if you are increasing temperature pressure so high, it is crossing critical temperature pressure, then system will not work. So you have to be below that. Okay, so T2, T1, and this is saturation line. Saturation line. So the saturation in left side one liquid, right side one gaseous. Okay, because energy H means internal energy high means it will be gaseous. So simple. Okay, so saturation vapor line, saturation vapor line, saturation liquid line, you can say. Okay, and this will be the purge dryness fraction, certain how much liquid is there, because inside envelope there will be liquid plus gas. So how much liquid percentage is there, will be like these lines will be there inside dotted lines I am drawing. Okay, so condenser, H2 equals Q1 plus H3. I have to draw this diagram, other than it will be very difficult to understand. This is condenser, this is your throttle valve, this is your evaporator, compressor is going like this, numbering like 2 1 4 3. Okay, so QH3, Q1H3, Q1 equals H2 minus H3, H3 equals H4, H3 equals H4, you can see the throttling happening, so there is no enthalpy change. Okay, it's isenthalpic process. Okay, so this is condenser. Now evaporator, expansion valve. Expansion valve means H3 equals H4, the enthalpy change is not happening. Okay, then evaporator, H4 equals Q2 minus H1, Q2 equals H1 minus H4. So this is called refrigeration effect. Okay, refrigeration effect. Okay, COP equals Q2 by W, H1 minus H4, H2 minus H1. Okay, so this is your coefficient of performance of the system. So mass flow rate of refrigerant, mass flow rate, mass flow rate W, then WH1 minus H4, it will be in kg per second, kg per second. Okay. Okay, thank you very much for today's lecture. Next day we will continue this lecture. Thank you very much.